Greetings, differential equation scholars, and welcome to video number 4 in our series on section 7.1 of your text on the definition of the Laplace transform. In previous videos, we've learned how we could use the definition of the Laplace transform to find the transform of a constant, the transform of an exponential function, and we've recently learned about the property of linearity of the Laplace transform that can allow us to find the Laplace transforms of more complex functions by applying our knowledge of the transforms of simpler ones. In this video here, we're going to take a look at an example of using the definition of the Laplace transform to find the transform of a piecewise defined function. So let us see if we can apply this definition of the Laplace transform as an improper integral to help find the Laplace transform of the following function. Our goal here is going to be to determine the Laplace transform for the piecewise function that you see graphed here on this slide. It's a function that has a value of 0 for values up to, but not including 2, and then starting at 2, has values that fall along this line of positive slope that goes through the points 2, 6 and the point 3, 9. And we want to find the Laplace transform for this piecewise defined function. Now, to do that, the first thing that we have to decide is what is this function's rule? So let's take a look at that. What is the rule for this piecewise function? Well, we're going to determine how to express that function in 2 steps. First, as we said, the function has 0 value for values of x that are less than 2. And for values of x that are 2 or more, as we said, those function values lie on this straight line. Now we can see from that line that as we go from 2 to 3, the y value goes from 6 to 9. And so that's going to imply that we have a rise over run of 3 over 1, or 3. So that's a line with a slope of 3. And it's easy to see if we extend that line down, its y-intercept would be 0. And indeed, the rule y equal to 3x does satisfy both of those points, 2, 6 and 3, 9. And so we now have the rule for our function. We're going to put those 2 pieces together. We're going to say that if x is less than 2, f of x is 0. And if x is greater than or equal to 2, f of x is equal to 3 times x. That's our piecewise defined rule. Now, what is its Laplace transform, we ask? Well, if we want to discern that, we must apply the definition. The definition says that the Laplace transform of any function little f of t is the improper integral from 0 up to infinity of the product of e to the negative st, called the kernel of the transform, times the function f of t dt. So we want to integrate this product of e to the minus st times our function f of t. Well, let's substitute in what our function f is. Now, as we do that, because this is a piecewise defined function, we actually have to write that integral from 0 to infinity in 2 pieces, because our function rule changes at x equal to 2. So between x equals 0 and x equal to 2, we're going to substitute in 0 for our function value, because that's what it is. And going between 2 and infinity for all values 2 or larger, we know that this integral has, that the function f of t has a value of 3 times its input argument. So 3t we'll write here. So this is our expression. But it's easy to see there that between 0 and 2, that integrand is 0. And so if we're integrating 0 between 0 and 2, this first piece will just disappear. The area underneath f of t equal to 0 between 0 and 2 is certainly 0. And so that'll just leave us then with this second piece here. But that's an improper integral, so let's write it in limit form. The integral from 2 to infinity is really the same thing as the limit as b goes to infinity of the integral from 2 up to b of 3t times e to the minus st dt. And so we must now evaluate this limit of the definite integral going from 2 up to b as b goes to infinity. And we must evaluate this rather testy integral that we see here. Well, it's not so testy after all, but we are going to need integration by parts in order to finish off this integration. We certainly do have a product of functions here. We have a linear function here, 3t, and an exponential function, e to the minus st. We can't do this integration directly, but if I let u be 3t, so that du is 3 dt, and let dv be e to the minus st dt, so that v is minus 1 over s times e to the minus st, that will allow us to integrate by parts. And we'll achieve the results here that we see here on the right, integrating the integral of u dv. We get a result of u times v, which is right here, minus the integral of v du. Now, the nice thing here is that this second integral is immediately solvable. It's an integral with respect to t, remember. S is just a constant for purposes of the integration. And it's going to be very easy to anti-differentiate this exponential function here now. So in the second integral, we'll factor out, we've got minus a negative 3 over s. We can write that as plus 3 over s and pull that out of the second integral so that we're just integrating e to the minus st from the second piece. That integration will introduce another factor of negative 1 over s when we do the anti-differentiation here. And so now we see we have the limit as b goes to infinity of minus 3t e to the minus st divided by s minus 3 times e to the minus st divided by s squared. So we've got two terms here. One of them has a t in the numerator that the other one doesn't have, and the other one has an extra power of s in the denominator due to the 2 rounds of integration that we've done on that exponential. And we want to take the limit of this. Of course, we've got to evaluate it. We found the antiderivative. We must evaluate it going between 2 and b. When we substitute in t equal to b into that expression, we'll get what we see here on the left. Here it comes. So minus 3b e to the minus bs over s minus 3 times e to the minus bs over s squared. That's from substituting in t equal to b into our antiderivative. But then we also have to substitute in t equal to 2. Now remember here, we're not substituting in 0 because of the nature of the integral that we're doing. We ended up with 2 as a lower limit here. So when I substitute in 2, minus 3 times 2 will give us a minus 6 here. And we'll have e to the minus 2s right here. So minus 6 e to the minus 2s divided by s. And then minus 3 times e to the minus 2s over s squared. So that's what we've got. Now, there's two pieces there, but if we look carefully at that, of course, we're going to notice that only at the upper limit do we have terms that involve the variable b that is moving in the limit. These terms, of course, here where we evaluated our antiderivative at 2, at t equal to 2, they don't have b in them at all. And so because they don't have b in them at all, what we can really do is pull them outside of the limit. Those are effectively constants. They're not changing as b changes. So we're going to have these two terms here at the end, really plus 6 e to the minus 2s over s and plus 3 e to the minus 2s over s squared. Those will be constants that'll be outside of our limit. But we still have to think about this limit here as b is going to infinity. So let's now consider the limiting behavior of these pieces here. There are two terms there whose behavior we need to analyze as b is going to positive infinity. One of those terms, the second of the two terms, is really minus 3 e to the minus bs over s squared, which we could write as minus 3 over s squared times e to the minus bs. Now, if we think about what's happening to this as b is changing, remember s is not, s is fixed. The only thing that's changing here is b, and b is increasing without bound. What happens to an exponential here, to this negative exponential, assuming that s is positive, and we'll assume that here, assuming that s is positive, then e to the minus bs, that is going to approach 0. And so therefore, if that approaches 0, then minus 3 over s squared times 0 also approaches 0 as well. So because that negative exponential tends towards 0 as b goes to infinity, we get a limit of 0. And that'll be the limit for this piece right here. But now there is another piece. And this other piece has a b that is multiplying the e to the minus bs. It has only one power of s in the denominator. That's not really important here because, again, remember, the 3 over s here is really just a constant. What we care about here is what's going on with b times e to the minus bs. The e to the minus bs, as we just said a minute ago, that's tending towards 0. The b is tending towards infinity. So we have a piece that's tending towards infinity. We have a piece that's tending towards 0. That would be what we refer to as an indeterminate form. But when we look at those functions and their growth rates, this is a linear function, a polynomial function in b, and this is an exponential. And as part of our theory about the growth rates of functions, and you can prove this using L'Hopital's rule, it turns out that in terms of their rates of change, this piece here, this exponential function, is approaching 0 so rapidly that the result is that the product of b times e to the minus bs is indeed going to go to 0 in the limit, because the growth, you might say in this case, the decay rate of e to the minus bs overpowers the growth rate of the polynomial b. And so because of that, this piece as well approaches 0 in the limit as b goes to infinity. So we've got two pieces up here then that are both approaching 0 as b goes to infinity. And what that means is the only pieces that survive are these pieces that came from the evaluation at the lower limit. So here we find our result. This will be the Laplace transform of our piecewise defined function. 6 times e to the minus 2s over s plus 3 times e to the minus 2s over s squared. Now, since there is a factor of e to the minus 2s in both of those, we could factor that out. and write the expression as e to the minus 2s times 6 over s plus 3 over s squared. That's our Laplace transform. Now, a curious thing to notice is that this coefficient that is in front here, we have this exponential e to the as here. Notice that this coefficient has the number 2 in it. It turns out that that's not an accident. It turns out that that's very closely related to the fact that our piecewise function really began to be non-zero valued at x equal to 2. Indeed, in a later section, 7.3, we're going to learn another theorem that can allow us to obtain the same result that we achieved here through means of another, what we call a transformation theorem. But for here, we've used the definition of the Laplace transform to find the Laplace transform of a piecewise defined function. So I hope that this video has been informative and instructive as you work on your homework. Stay tuned. Coming in about a day, we will have some additional videos starting in on section 7.2 as we continue our discussion of the Laplace transform. I thank you very much, and I wish you well.